exponential log derivatives is there's 4 different types, and I'll be able to show you how we get the derivative of each one. So there's 4 types. We've got functions that are e to the x, right, that type. We've got functions that are a number to the x power, like 3 to the x. And then we've got log, regular log, and then we got natural log. And so those are really the 4. First, what I'm going to do is show you how we get each one, and then do one example of each type. So, well, let's go ahead and jump in. The first one is e to the x. To figure out the e to the x. This is the only one I kind of got 2 ways to show you. Each of them needs a little something else, and so we're going to get to where we need to go, and then I'm going to tell you, oh, this is kind of what would happen with this. The first way I can show you is using the limit definition. And so what we can do, the derivative of e to the x. So I'll change this, we've been doing a lot more. So I do f of a plus h, so when I put the a plus h in, minus f of a, so the e to the a, when I put a in. You can leave it as x if you want. All right, and so what I'm going to do is I'm going to factor out an e to the a. Factor out an e to the a. Now, just like x squared times x cubed is x to the 5th, like I can break it down. That's what this really is right here. So it really means, this really means x to the 2 plus 3, like I've added the exponents. And so right here, if I factor out an e to the a, well, it was really e to the a plus h, which really means e to the a times e to the h. Because when you multiply, you add the exponents. And so I factor out an e to the a, e to the a power, I'm left with e to the h. And then here, if I factor out e to the a, I'm left with minus 1. And then this is where, on this one, I'm going to make a little conclusion. This is a limit that we know. I mean, we haven't done much with it yet, but this is something in calculus that we know. This limit is like sine x over x is at 0 is 1. This one, the limit at 0, is also 1. And so we get e to the a. Now, for our purposes, right, whenever we used to the derivative of like x squared, we got 2a, and then the derivative was really 2x. So what this tells us is the derivative of e to the x is e to the x. So this is one of the most important conclusions about exponential and why it's important. There's some others that you probably did in, when did you do exponential? Maybe like algebra 2 sometime, algebra 2-ish. But for calculus, this is why it's so important, is the derivative of e to the x is e to the x. All right, now there will be some differences with chain rule, but this is really the only, this function, the derivative of e to the x is itself. Off the top of my head, I can only think of one other function, 0, where the derivative of it itself, is itself. So, let me show you another way to do this, and what we're going to do is I'm going to call y equal e to the x. And what I'm going to do is I'm going to do a natural log of both sides. And so I'll have this, natural log of y, the ln of e cancels and we get x. And what I'm going to do is differentiate implicitly. Okay, what we've been doing. On this one, we'll have to make a little bit of a conclusion about something we don't know yet, but so it's ln of y equals x, and what I'm going to do is do d dx to both sides. I'm going to differentiate implicitly. So the right side is certainly 1. And the left side, this is where I'm going to tell you in a few minutes, we'll find out the derivative of ln y. So the derivative of ln y is going to be 1 over y. Really chain rule. It's a y function, so the derivative, I need to add in the dy dx. It's 1 over y. We'll find that out. That's each of these we need a kind of a conclusion that we haven't really found out yet. So then I'm going to multiply both sides by y to get dy dx by itself. And so dy dx is y, 1 times y. Now that's correct in terms of the variable y, but we actually knew up here that y was e dx, and so I can replace y with e dx. And that's just another example. Again, we had another derivative of natural log, but another example to show you that the derivative of e dx is e dx. Let me write it down for us in the table. So each of these I have a table that summarizes. And then I'll see if there's any questions. So we just found this out. The derivative of e dx is e dx. Now each one of these in the table, then I'm going to show you the chain rule, right? Because it's not always e to the x. It might be e to the 3x. So if we're doing the derivative and it's not e to the x, e to u, it means u is something else. So it could be like this, e to the 2x squared plus 1. This would imply you need the chain rule. So you know how normally, like I say, all right, it's chain rule, like inside here, it's like something other than x, right? Right there. For exponentials, it's if the exponent is different. So it's a little bit of a change. Normally you're looking like the base of the function. For exponentials, if the exponent is anything but x, then you'll need a chain rule. So in this case, the derivative would be e to the u prime. That's another way to say du. This is another way to say u prime. So that just says you need to do a chain rule. You keep what's here, then you do the derivative of the exponent. So let me show you one example of that. Any thoughts before?
So even if it's like e to 2x?
Yes, chain rule. So here, this is a simple one we could do. E to 2x. Oh, this is good. I'll do this even before that one. The derivative is itself. E to 2x. Right? So really, if I go back to really what I've been talking through with chain rule, this is my f, and this is my g. And so the derivative, I do f prime. The derivative of e to the x is e to something. Then I keep the g, the 2x. Then I do the derivative of g. In this case, you're looking at the derivative of the exponent, 2x, which is 2.
The 2 go up with the exponent? Or
It is with the e. So I rewrite it like this as my final answer. Yeah, thank you. That's a good question to get us going on that. Yeah, so these are actually pretty simple. You'll like these overall. You write exactly what's there, and then times the derivative of whatever the exponent is. So let's see it over here. This means derivative with respect to x of e the radical x. And so, you're not going to do what I've done that one. E is really the f, and the exponent is my g. And so the derivative is f prime of g prime. So the derivative is e. Derivative of e the u, e to anything. I keep the g, and so that's the radical x. That's f prime of something. That's the g I just kept, radical x. And then times the derivative of radical x. So let me do that one off to the side. We know this one, it's just we haven't done too much recently. We change it to the half power. We then do the power rule. No chain rule needed here. 1/2 x to the negative 1/2. And so then I'll put this down as a positive exponent like that. All right, now I'll just bring it over here. So it's 1 over 2. I'm going to write it as radical x. Because x to the 1/2 power is the same as radical x. So similar chain rule stuff, just you see it in a new context with exponentials. Okay, next I'm going to go on to a to the x. So before that, any questions on e to the x? Sounds good. Let's move on to the next one then. The next one is a to the x. So this is a being any number. It's like 2 to the x. It's again exponential. It's an exponential function, but it's not e being the base. It's just some other number. Any number being the base. One thing to note, sometimes later in the year, it's tough to remember all these rules. I'll have students do this. Do power rule on this. There is no power rules only if it's x to a number. This is a number to the x power. Okay, so this is not correct. Do not do that. Alright, so really any number to the x power. So to show you this one, we first have to make a note that a to the x is actually equivalent to this. E to the natural log of a to the x. Because what we could then do is these would cancel, like e to the ln, and it would just be a to the x on the right side. So what we're doing is just writing it in a different form. I'm writing it in a different form so that then I can use the rule we just did with e to the x. Okay, so let's write here. So the derivative of a to the x is the derivative of this one, e to the ln of a to the x. Okay, so what I just did, that's just an equivalent form. Now before I do the derivative, let me just, so I'll write it again here, d dx. I haven't done the derivative yet. Property of log says that if there's an exponent, we can bring it down in front. So just in this expression, ln of a to the x, I'm going to bring down the x in front of the ln a. Okay, so that's just a property of logs. Bring the exponent down. Okay, now I'm going to go ahead and do the derivative. And we just learned the derivative of e to the x. So I'm doing that, but I'll have to do a chain rule. So the derivative here, we'll go ahead and evaluate, is itself. I write everything. E to the x ln a. It's an x. Times, so this is where I'm doing a chain rule. So actually I already did. This was f prime of g in my chain rule. I already did f prime of g. Now I gotta do g prime. So I gotta do the derivative of this. With x ln a. Now, ln of a is a number. A is a number up there. So ln of a is also a number. It's like ln of 2, it's a number. So really a better form would be ln of a times x. It's like if I was doing the derivative of ln of 2 times x. That's a number. Times x. So it's like derivative of 3x would be 3. Derivative of ln of 2x would be ln of 2. And so the derivative of ln of a times x is ln of a. It's really ln of a times 1. Right? Just a number in front times the derivative of x, which is 1. Let's see if there's anything else I want to do on this one. Oh, so then, okay, so that's it. Now I'm going to write it in a different form for our purposes. I'm going to move this x back up. Ooh, e to the ln of x, ln a to the x. So property of logs, I can put the x as a coefficient, or like that, or I can move it back up to the exponent. And now, guys, what I'm going to do, this was the original thing. E to the ln of a to the x was the original. It was a to the x. And so, I get that the derivative of a to the x is a to the x ln a. So what I did again was just I changed how it looked. so that then I could use the exponent rule for e to the x. Then I did the derivative, got this. Move the x back up here, and then change this back to what it originally was. So guys, what this says so far, we got e to the x is e to the x. That's the derivative. For a to the x, it's kind of the same thing. The derivative is a to the x. But you got to have ln of a after it. And if it's chain rule, it's a to the u ln a times that u prime. So let me give you a simple example, and then and then we'll do this one. 2 to the x. No chain rule here, just 2 to the x. The derivative would be 2 to the x. That was this. ln of a, which is 2. Okay. Now, if I could, watch this. Remember when I did e to the x? I want to show you, these are actually the same rule. Watch this. The derivative of e to the x, if I use this rule, is e to the x ln of the base a, which in this case is e. But what's ln of e? It's 1. Ln of, it is really a base of e is 1. So what I'm just showing you is this rule actually does both of the rules we did before. It's just what's nice about e to the x is this part always becomes 1. So there's actually only one rule for this. It's this one. But the e to the x one is simpler. We don't need the ln part. Let's do this one. Any thoughts? So, I mean, this is the basic one here. 2 to the x ln 2. Anything I can clarify on that, though? So let's do one with chain rule. Differentiate this. So y prime. I'm following this rule right here, and I will need a little chain rule. The reason I know that is because, again, the exponent is not x. It's x to the 4th. X to the 4th plus 2. Okay, so y prime is going to be a to the x. It's pretty simple. I just write the exact thing that's there. So really with chain rule, again, here's what I've already accomplished. I already did f prime. That was 5 to some exponent. And I kept the g. That's the x to the 4th plus 2. Times, then the g prime is the derivative of the exponent, which is 4x cubed. None of those are like terms, so there's nothing I can simplify. Oh, I forgot one thing, sorry. Ln of a. You know what? I'd actually rather write the ln of a first. I'm sorry. It doesn't matter, actually. I'd rather write the ln of my base 5 first. But I could have put it after. Sorry about that. Again, nothing can combine there. So f prime of g, that was this, and then the g prime was over here, the 4x cubed. And then I also need ln of my base, which was 5. Sorry, forgot that at first there. Let's see. How are we doing? Any thoughts on that? Yes, Chris.
So is that just like the end of it?
Yeah. All right. Some of these, there's not much to simplify. So. I think I'm just going to skip the next one. It's tangent line, but it's the same. It's actually no chain rule. It's the same thing. But we've done chain rule. I'd rather do the practice with that. Let me just skip to the last two here. So that's really, there's really one rule for e to the x and a to the x. But the e to the x one, you don't have to write ln of e because it's always 1. So those two go together. Well, flip the page, and these two as well, these two go together. There's really only one rule, but there's a simpler one when it's natural log instead of any log. Okay, so we flip it over. We're going to do the derivative of ln of x. ln of x. what I'm going to do is implicit differentiation to get this one. So I'm going to say y is ln of x. That's my function. Y equals ln of x. I'm then going to do the change from x log to exponential form. I used to describe it, rewrite it. It's really a base of e. The arrow thing that I do. This one. It's been a little while, but I'm just changing from log form to exponential form. It's e to the y power equals x. That's what we get here. Again, it's just changing forms. Log to exponential form. Usually if it's an equation you're solving, you have to change form of log. When logs are only on one side of the equation, I change forms. So now what I'm going to do is I got this, e to the y equals x. And I'm going to do implicit differentiation. So I'm going to do d dx to both sides. We'll do the derivative to both sides, and this will give us our result. Okay, so the right side is 1. The left side, the derivative of e to the y. Well, we treat it like e to the x. Okay, so I will have to do a chain rule. So I treat it like e to the x, it'd be e to the x, in this case e to the y, times the inside, the g part, is y. And so the derivative of that is dy dx. So really, derivative of e, kept the g, which was y. Then here's where I usually draw an arrow things, times the derivative of y, which is dy dx. Okay, and we solve for dy dx on these. So I'm just going to divide both sides by u to the y. Now that is it. That's dy dx in terms of a y variable. But what's nice is we actually know e to the y right here is x. So I'm going to replace e to the y with x. That's the derivative of a natural log. 1 over x. It's one of the simpler ones. Like e to the x is e to the x. The derivative of natural log x is 1 over x. And so then, if it's anything but x, then it would be 1 over u times du dx. 1 over u times u prime. We need a chain rule. And so I think let me just do this example to illustrate this one. Okay, so if it's straight up natural log x, the derivative is 1 over x. But as soon as this x becomes something else, then we'll do a chain rule. So let me show you on this one. Do the derivative with respect to x of natural log of x squared minus 4x plus 8. Okay. So notice here, when you're doing the derivative of natural log, the answer, sometimes students write this, like 1 over ln. When you do the derivative of natural log, there's not going to be a natural log left. It's 1 over x. Now in this case, it's 1 over something. This is where I'm going to do a chain rule. So derivative is 1 over something. I keep the g, the inside. And so that goes right here. So 1 over x, but now it's not x anymore. It's 1 over this, the g. That one is my f, this is my g. Times g prime. So then times the derivative of this, which is 2x minus 4. And that's part of the numerator. That's not in the denominator. You can leave it like that. That's acceptable. Sometimes I just bring that into the numerator. Like this. I'll write it like this, a little more compact, but either one's fine. Also, I want to mention sometimes you might be able to cancel things sometimes with this. So look, sometimes these might be a factor or just cancel a 2 or something. So on these, just watch for a cancel. Okay, that's it for natural log. And I got regular log. Anything I can answer on that one? let's go down to the bottom and I'll show you the last one. The last one is any log. So really, guys, before, natural log is really a base of e. It's really like log base e of x, but we change it as natural log. We don't write that. So really, now on these, we're going to have any base other than e. So the base will be a, and it's a number. And I'll show you how we get this derivative. Now for this one, we're going to need the change of base formula. That was definitely algebra 2. Do you guys remember doing that for logs, changing the base? Anybody? No? Well, change of base formula says this. So let me write it here. So we're going to do the derivative. I'm going to change this inside though. I'm going to use the change of base formula. So what that says is you can change this into 2 logs, one with x, one with a, and you can choose any new base. What I'm going to choose is natural log as the base. Okay, so I'm not sure how much you did of this in the past, but change of base formula. And that's really what I did there. You can change it into log base anything. I think usually we put like b, really a different number, of x over log base the same number. Usually I think we put like b. You can change it into any base of 2 logs that you want. It can make the problem easier to compute sometimes, and that's why that one's there. And so for our purposes, it makes it a lot easier. Because I don't know the derivative of that, but this one, I do. Okay. And what I'm going to do is, let me actually first write this in a better form. Suppose I had ln x over 2. By the way, I could do quotient rule on this, but I'm just showing you I don't want to. But if it's ln x over 2, isn't that really 1/2? It's really 1/2 here. And so I'm going to write 1/2 ln x. That's a better form to write it. I won't have to do quotient rule. So over here, I'm going to do the same thing, a better form. It's really 1 over ln a. So I'm going to write it as a better form, 1 over ln a times ln x. Just like on that one, I brought the 1/2 out, I'm bringing the 1 over ln a out. Because remember, a is a number, so ln of a is also a number. So now that that's a number, it's like doing 3 times the derivative of ln x. The derivative would be 3, and I do the derivative of ln x. All right, since this is just a number. And so I'm going to do the derivative. Now I'm doing the derivative. I bring down the 1 over ln a, just like I would bring down the 3 here. And then the derivative of ln x is 1 over x. I combine those. We traditionally write the x first. So it's 1 over x ln a. I think the box is on the next page. So you see, each of these kind of like builds upon itself, and this one change of base. There's usually a little trick of some sort, a little clever tool we can use. Then I was able to do the derivative because I knew the derivative of ln x on this one. Now it's just a number that came down. Derivative of ln x is 1 over x. So let's write it down on the next page. Here's the box. So the derivative of log base a of x is 1 over x ln a. All right, let me show you. If it was, what was it? Natural log. It's actually the same rule. It'd be 1 over x ln of the base e. ln a, base a is e. But again, that's just 1, and so it becomes 1 over x. So it's just the same rule, but the ln one is slightly simpler. And if you need a chain rule, log base a of u is 1 over x ln A, 1 over u, I'm sorry, 1 over u ln A with the chain rule of du dx, u prime. Yeah. All right, I'll finish these two and log differentiation tomorrow.